Okay. All right. So what I want to do today is the simplest possible physics-based system I can come up with, where we can already talk about all the physics and math. And that example is a harmonic oscillator. If you have taken some physics class, you might have done it already. So let me tell you what the setup there is. So it's really the simplest possible physics-based system you can possibly imagine. I cannot make it any simpler than that. Let me put it that way. Let me check if this is for the recording. It seems it is, so we are good. So it is in 1D, one-dimensional kind of thing. So you are simulating something that lives really not even on a flat land, but like on a line land. When you have some origin, some zero, this is like an x-axis. And that's all there is. That's a very unusual kind of case because usually you have physics in 2D, right? Like the Angry Birds kind of physics, like on a phone without any third dimension, or more commonly in 3D, right? This will be a 1D case. Furthermore, it will be even simpler than, even if a further simplification I can do it. It has 1 degree of freedom, DOF, okay? So there is only a single mass point, and that's also like very unusual kind of thing, right? Typically, like with animations that's showing on Monday, you have some like cloth which is like 10,000 points, and they move in 3D, right? So those are like the real things we'll be eventually simulating. But this is a very simple toy case, but it will be already quite interesting. And what this mass point, so this is a single mass point in 1D. So the beauty of this is that to describe the position of the mass point, I need only one number, okay? And that one number, the one problem here is that I cannot point to things. I can do, so the one number, I can do this. The one number is just a coordinate on this single axis, okay? Well, I can use my mouse, but then it won't be recorded. Unfortunately, on the iPad, there is no cursor or anything. I actually sent the GoodNotes guys a message, like, could you put their laser pointer thing, which they actually have, but the thing is that it detects whether it's connected directly to the projector and then they turn it on. But this is connected to a projector via a Mac, so that it doesn't do that. All right, so just yell at me if I'm pointing at something and you don't know what I'm pointing at, okay? But the point is here that, okay, so the current state of the system is represented just by a single coordinate, okay? So what we have, so maybe I can just do this, right? So we have some mass point. It can be here, right? In which case this will be some value of the x-axis like 5, right? Or it can be somewhere else. It can be like here, in which case it would be like 6.7 or something, okay? So so the motion basically means the state varying in time. Okay, so we can put it as a function x of t, where t is time. T is time. Okay, so the x is a function from r to r. So I'll also use this lecture to kind of introduce the way I like denote things. So this means the x is a function from real numbers to real numbers. This input r means time. This output means the position on this axis. Wherever on this axis it is, that's this thing here. Maybe I can point my way around like this and then just undo it. I'm testing the setup for the first time, so well. So the x is just a regular 1D function, right? That's the bread and butter of like calculus, no multivariate business. So I can, with any motion, I can visualize like this, right? Start somewhere, then it does something, and that would be some motion, okay? Some function x. The only thing that it cannot do, it cannot go backwards in time. It cannot do something like this, right? You know that would not be a valid function because here the point cannot travel back in time. That's why. All right, so that's the position. What is velocity? So we'll slowly build up all the physics-based concepts, right? So in this case, velocity is something very simple. What is velocity? I guess this is also an opportunity for you to demonstrate your activity things. I tend to ask questions. I like to invite some discussions. So who wants to? Okay, maybe raise your hand and then I'll pick somebody. Okay, I'll pick you. That's exactly right. Rate of change so of the x here, right? And mathematically, what is the concept, Junior? Exactly, it's the first derivative. That's right. Also, so velocity is typically denoted as v, and it's also a function of t, and it's a function which defined really as first derivative of the position. So this little dot here, that's usually what denotes differentiation in time. Okay, there are other ways how you could denote it. You could do this, or some people would prefer like this, like partial derivative kind of notation at t. I'll be mostly using the dot because that's what usually used for time derivative. Okay. So that's velocity, and then the other thing we will need is acceleration. What is acceleration? Very similar kind of idea, Magdalena? Exactly, so that's a derivative of the velocity. So typically we denote it as a of t. It's again a function of t, okay? So both the x, v, and a, they are all functions from r to r, okay? So at is the derivative of velocity, and because velocity was already derivative of positions, that means second derivative of positions, okay? So that's the basic setup, and now I need to say what is the physics of the system, okay? What forces are acting on my system? So here the setup is like this. So if this is my 0, okay, so again I'm still in one dimension, here is my x variable. So the idea is that my mass point, so let's say it's here, the mass point, we'll imagine that the mass point is connected with a spring to the origin, okay? And that's a spring that would ideally like to be length 0, okay? So the spring would be most happy if the point was right here, okay? If the point is somewhere else, like here, then the spring is extended and wants to push back, okay? So mathematically the spring force, so we need the concept of force. So the spring force, or physically, the easiest model for spring force is Hooke's law. Do you remember that from some physics class? What would be the force? If I give you, so this is the current x, t coordinate of that point, what would be the force according to the Hooke's law that acts on that particle? You did physics, right? So you know that very well.
The displacement times the spring constant.
Exactly. With minus, exactly. That's right. You are James, right? I don't know, I keep forgetting such a simple name. So yes, so what you said, if I write it in equation, so then the force at any point x, this is important, the force depends on where, I really need the pointer here, oh no. The force really depends on where that point is, okay, on the x coordinate. And that force, just as you said correctly, is minus k times x, okay? Where k is the stiffness of the spring. And let's just not make things more complicated. Let's just say that the stiffness k is 1, okay? Just to keep things simple and keep the formulas easy to work out, okay? So intuitively, it kind of makes sense, right? If the point is like here, let's say this xt equals, I don't know, 5, then the force will be minus 5, which means that the force acts in the opposite direction, that the force is pushing it back to the origin, okay? That's why the minus is there. The minus is kind of important, okay? Now, if the point was, instead if the point was here, then the x coordinate would be negative, would be like minus 6, right? So then the force would be plus 6 and would be pushing it the other way around. So this direction here, that's the direction of the axis. So that's basically like the only direction you have in one dimension. In 2 dimensions and 3 dimensions, this all becomes much more complicated because then you have many directions in which you can go, many directions in which the spring can stretch, right? In 1D, it can only stretch to the right or to the left, and that's it. So you only need a sign to distinguish these two things. If it's in 2D or 3D, it's much more complicated because it can point in many directions, and things get actually much more complicated in that case. So let's stick with this simple example, which is already kind of interesting. So now I told you what the force is acting on it. So now we can completely write what is the motion according to Newton's laws of motion. Okay, so specifically we will use the Newton's second law. What does Newton's second law say? Maybe raise your hands and I can pick somebody who didn't get a chance to speak it. So Radish? Exactly. So basically that says F equals ma, right? So what does that mean in our case? So we know what the force is, right? Maybe I will make it consistent and make it lowercase f. So the one important subtlety is that the force actually depends on the current position where the mass point is, right? So the f of x of t, and that is proportional to mass times the acceleration, which also depends on t, okay? So this will lead to a differential equation. That's why I'm putting the t's there, so it's clear. So let's make things simple. Let's assume that the mass is 1, okay, to like really simplify things as much as possible. So in that case, and we know, of course, so in that case, this becomes that the force of x of t is the second derivative of x at t, okay? And in our case, we know that the f of x of t is actually very simple. In our case, so this would hold in general for any forces that are position dependent, okay? But in our case, we said that the forces are going to be just minus, and we even said the k is 1, so this is just minus x of t, okay? And remember, the x is still a function, okay? This thing, that did not go away. X is a function, okay? So the thing that we have here is exactly a differential equation. It's a second order ordinary differential equation. Why is it second order? It's the only tricky bit there, I guess. Exactly, because here I have the second derivative. Yeah, question, Margaret? Exactly, that's where the minus came from. Yep. And the minus is kind of important, right? Because if you forgot the minus, then then the force was acting the other direction, you would not get an oscillator, but something that just shoots away. If that makes sense, right? Because the key thing is, if you are here, then you need the force to go back. If the force was trying to just push it in the other direction, in this direction, then it would get here, and we're going to push a bit even higher force, and would just like shoot off, right? So that would not be a very interesting example. So that's why the minus there is quite important, even though it looks like a minor detail. It's a detail that actually matters a lot, okay? All right, so how do we solve ordinary differential equation second order? So the standard trick there is to convert it to a system of two first order ODEs, okay? So that's a pretty standard trick done in differential equations. So what we will, and the way to do it, so what we will do, we'll convert, let me go a little bit slower, to first order ODEs, but then they will be two of them, okay? That's kind of the trade-off. You cannot get rid of the two kind of thing. So the way to do this is by introducing the velocity. So we already talked about the velocity, but we just say that the velocity is, or let me write it like this. What we established before is that the derivative of the positions, the first time derivative of the positions is velocity, right? And the trick of converting the second order ODE to two first order ODEs is to add exactly this equation as an additional equation, okay? Because if I do that, then instead of the x double dot t, the second differentiation in time of x, what I can write instead, and that's really where the tricks come to play, is that the derivative of velocity, and then I will, what happened? I pressed the wrong thing. So that's the f of x t, okay, which in our case is just the minus x of t. Okay, so now what we have here, so previously, let me just make this very clear. What we had here was a single differential equation of a second order, okay? What we have here are two differential equations of first order, okay? Because there is only first order differentiation, only first derivative. So that's a standard trick that's often done. And because dealing with two equations might be somewhat cumbersome for notation purposes, I will also use a new variable z, which will be a concatenation of the position and velocity, okay? So I'll say that z is a system state. It's a two-dimensional real vector. Both position and velocity are just numbers. They can vary in time, so we can plug functions in there. But the point is that this really is two numbers, and we'll call it the system state, or state vector, if you will, okay? So that at any point in time, you can say that the system is represented by both position and velocity, which fully captures the system as far as this first order system of ODEs is concerned. Just to make it clear now, we are solving now, oops, some more practice with this. So before in this case, oh no. In this case, we were solving a single equation for a single function x, okay? Now in this case, we are solving for two functions, x, which is a function r to r, and v, which is also a function from r to r, okay? So that's kind of the trade-off, like you get it to first order, but you pay for it by solving for two functions instead of one, okay? But this is actually a good trade-off to make, okay? So let's write it all in terms of this state variable, okay? So, oh, look what I can do actually here. It's kind of cool. So I need to go to another page, and I think we can do like this and do copy. Then go to another page, and here do paste. Except it doesn't move. There we go. All right, so let me rewrite this in terms of the state variable. So the derivative of the state is now can be written like this: 0, 1, minus 1, 0, okay, times z of t. So the formatting is ugly, so let me improve that. Z t equals this, okay. Where did this come from? Well, because this is, I can write, this is a 2 by 1 kind of matrix, two-dimensional vector, okay? This is a 2 by 2 matrix, and this is a 2 by 1 thing again, okay? So this is like a very basic linear algebra kind of thing, two-dimensional vectors, and we have a matrix there, okay? And indeed, like this zt is x and v, right? So of course, the z derivative, let me put the t back there to make it like super clear, x derivative t, v derivative t, right? How do we differentiate vector functions? Well, by components, okay? Nothing too crazy is going on here, okay? If anything is unclear, then just yell at me and I will try to explain again. Magdalena? Oh, okay. So let me try to explain that. So this, I really wish I was able to point to things. So basically, I wanna take this. There are two equations, and I want to write it as one equation, okay? But that equation will contain vectors, okay? This will make the notation more concise. It's really just changing the notation. So what I say, we introduce this z variable, the state variable, which is a vector which contains both the position and the velocity, the x and the v, okay? So maybe it helps if I like write this out like this. So I can take this system and I can rewrite it like this. It's really just like a formatting kind of thing almost. It's like a silly semantics. So I can write it like this. And here will be the same matrix. And here is gonna be xt and vt, right? If you work out this matrix vector multiplication, what you will see is that you are getting here exactly, so you get a vector vt and minus xt. But see, this is exactly what we had here. bt and minus xt, okay? That's the same thing as here. Okay, that's I guess the only tricky thing, right? What is this funny matrix doing there? But that funny matrix, that's actually the key to this. And this funny matrix is actually a very special kind of matrix. We will have more to say about it later. It's the canonical symplectic form, but that doesn't matter right now. That will matter later, okay? So does it make sense now? Where did that? Yeah, so that's really just, so all I did here is rewrote these two equations in one matrix vector equation, and the matrix vector equation is kind of neat because what I can do, I can then write this simply as z dot t equals a z t, where guess what the a is? The a is exactly this matrix, okay? That's my a. So that's kind of, that's what I wanted. I just wanted to get this concise notation, and this is what you typically get to see when we talk about system. That's a system of linear ODEs, ordinary differential equations. Okay. And this is a very interesting thing to think about. I would like you to get a geometric intuition of what this means, because believe it or not, this has very beautiful geometric intuition. So all of these things, okay, you can think about it purely like algebraically. It's about a mathematical puzzle. Like I need to find this function z. So now z, actually, if I write it explicitly, z would be a function of this form, right? For the time variable, this one, it returns a 2D vector of positions and velocities. That's what the z is, right? And now the mathematical puzzle kind of viewpoint is that I give you a matrix A, right? It's this matrix here. And what I want you to do is to find a function z such that the derivative of z happens to be equal this matrix A times z for every t. That's the deal here, okay? And that really means finding the motion for all times, okay? Starting from time equals 0. So let's what is the geometric interpretation of this? Geometric interpretation or intuition. So maybe let me erase this, if you will. Let me make the eraser bigger. It's cool. Smaller. Okay. So first of all, what is A times some vector? If I have some vector, let's call it x and v, what do I get back? What is the, so we will start by figuring out what is the geometric meaning of the AZT. That's the easier part. In other words, what does the A matrix do geometrically? It's like this funny kind of thing, right? That like came by this like funny substitutions, but it's something that has a very clear geometric meaning. Well, first we can just compute it, right? If I do A times multiply xv, this is my matrix A, it's a 2 by 2 matrix. What do I get as a result? That's easy. Magda? That's exactly right. Yeah. So in terms of the x and v, that's you can say exactly what is in terms of x and v, right? In terms of x and v, it is v minus x, right? And I think you had exactly the right geometric intuition that it like flips the order and also changes the sign, right? So let's try to draw this. What does that mean? So if I give you some vector with coordinates x and v, the v is again kind of like for velocities, right? So this is x and v. So if I give you a vector like this, so it's a vector of coordinates x and v, how will the how will the A transformation of, let's say this is the Z, right? Then how will the AZ look like in that picture? I know it's harder to verbalize it, right? So let's see what happens, right? So the x coordinate happens, so v was this much, right? So that now goes on the x-axis here, right? And v was this much. No, x was this much, and that becomes now minus v, so that goes here, okay? So I get here, and if I complete this thing and get a vector, so this is my a z vector, okay, or if you will, a xv, okay. So what is the name for this geometric transformation? Rotation, exactly. And this is no surprise. If you remember from like some basic graphics class or something, in general, rotation in 2D, so now we are talking about 2D vectors, so now we all of a sudden came from 1D to 2D because we are converting the 2D ODE to 1D2 ODEs. The rotation in general, what is the general form of a rotation matrix in 2D? In general, for any angle alpha. Exactly. Cos theta minus sine theta, and cosine theta. That's exactly right. So that's the general form of rotation matrix, right? So we can see that A is basically nothing but rotation by how many degrees? Negative. Who said negative 90? Because that's right, by minus 90 degrees. Okay? And that's just because it rotates clockwise, okay, as opposed to the standard mathematical convention, the positive angle rotates counterclockwise, okay. So yeah, that's the geometry of A, okay. Now, what is the geometric meaning of the z function, and especially this z dot t? So what does mean the z dot t geometrically? So maybe I'll get rid of this, if that's okay. So this was just the geometric understanding of what A is. So now we have already established its rotation. And now the question is, how does the z function look like, and what its derivatives means? Okay. So what I can do is I can draw this space of positions and velocities. So the x is the positions, v is the velocities, and this is sometimes called the phase space. Okay, that's the diagram of both positions and velocities. Okay, and any function z, if I say there is some function z, okay, I always kind of assume that the time starts at 0 and keeps going on further and further. The time has this funny property that doesn't go backwards, so it needs to start somewhere. You might as well say let's start at 0. It kind of doesn't matter when you start measuring the time, right? But it's annoying. I need to disable those later. So then the function z starts somewhere. Okay, let's say that this is z0, and the function is basically just a two-dimensional curve. Okay, it's kind of nice. Do you see the? It's actually pretty low latency. So the curve can keep going arbitrarily. Okay, so at any time t, this will be the zt from t going for t going. Oh, I can also do different colors. It's kind of cool. So this would be t equals 0, right? And as the time increases, some point travels along this curve. Okay? That's kind of how you can look at the z function. Now, what I want to get to is what exactly is the geometric meaning of the time derivative of z, what this intuitively means. Sure enough, we know exactly what that means mathematically, right? That's what it is, right? That's the derivative of both of the components. But what does it mean on this picture? When I like draw this curve thing. What is the z dot of t geometrically? That's because I want to give you an intuition for what these things mean, as opposed to just the hard math. Any ideas? So the idea, like as I was drawing it here, the idea is you can imagine the z function as like something traveling along that curve, right? Some sort of like a little car in flatland going on. Yep.
So is it, excuse me, is it the slope at some point?
Exactly. Yes, it is. So let's. That's right. But let's work through the details some. So maybe one way to kind of see that is to invoke the actual definition of the derivative, right? How is derivative defined? It's a limit for some parameter h going to 0 of z t plus h minus z of t divided by h, okay? That's the definition of a derivative. You cannot disagree with that. But my point is to show the geometric intuition on this, okay? So let me draw a less cluttered example of the same thing, of the phase space. So this will be the same thing. I just want to do a less, I got a little too excited about the fact that it can go anywhere, okay? So let's do some simpler. By the way, also notice that this thing can now easily self-overlap. Okay, that's the difference from like a 1D function, because we have a 2D function. The time parameter sort of just tells me the speed of travel, or the time really, right? So now it's clear that this now can go over itself. Unlike this x thing, right, which could not. It could only go forward. Okay. Because this really is nothing but two functions, right? One for x and one for v. I could also like give you another v function. Now, this cannot be arbitrary. That needs to be the derivative of x. But it's just another function. All right, so let's say we have some not that crazy of a thing, okay? So this will be my z0, two-dimensional function. This will be z of t. And let's say h is something, okay? So this will be zt plus h, okay? So then what is zt plus h minus zt? That's a vector, right? And that's a vector which points like this, okay? From zt to zt plus h, okay? Because from the point zt plus h, we subtract zt, so we get like this little vector pointing in that direction, okay? So again, I assume that you know a little bit about linear algebra, affine spaces, points, and vectors. That's like the basic graphics or geometry stuff, okay? Well, and then the whole idea of this limit thing here is that you are making this h smaller and smaller, okay? So actually this is you can say, oh, this is too big h, so you can actually put the smaller h and make this arrow even smaller, okay? But so that it doesn't disappear, that's why you divide by this h here, okay? So that's really the idea of a derivative. So what you get at the end of the day after the limit process is, is this. So if your zt is here, then the derivative z dot t is the tangent vector at this particular point, okay? And actually, as we are at it, so the direction is kind of clear. The direction needs to be tangent, okay, to the curve. If the curve happened to be a line, then the tangent vector will be exactly in the direction of the line, okay? And the other interesting thing is the magnitude of this vector. So this is my way of denoting the Euclidean norm, okay? Because I guess because it's the first lecture, I should tell you what exactly that is, right? So the norm of z is the square root of x squared plus b squared, okay? Euclidean norm. So what is the geometric / physics intuition of the magnitude? So the direction is clear, right? The direction is the tangent. So kind of the linear, the best possible linear approximation in infinitesimally small neighborhood of the point zt, right? That's what the direction of the z dot t is. And the magnitude, what does that mean? What do you think? It's just hand wavy, no hard math. Concur?
It's strength, I would say.
It's what?
Strength.
Strength?
Yeah. Is that what you're asking? Is that what you're asking?
No, I'm asking what is the meaning of the norm of the derivative of zt. So, like for example, if this is a number, right? First of all, that's a scalar, right? It must be a non-negative scalar, right? Because it's a norm. So if it's something large, if it's big, what does that mean? If it's small, what does that mean? It has like a very beautiful physics / geometry interpretation. It's
I would call it a strength of the vector.
Yeah, that's one way to look at it. Magdalena? No, curvature, you're right that curvature is a closely related concept, but to get a curvature, you have to do the second derivative of that thing. But you're in the right area. You are basically realizing that this goes into like very basic differential geometry of curves.
Is it the rate of change?
Exactly, it's the rate of change. Exactly. AKA speed, instantaneous speed. Okay, so as I was drawing before, let's take another one here, right? Another z0. So this thing can travel, okay, and it can travel fast or it can travel slow. Okay, imagine it's like a little car in 2D, and it can go the same path with different speeds. Okay, instantaneous speed, and that's exactly what this thing is. Okay, so let's write it here. Instantaneous speed. Actually, since you brought up the differential, we will not go like very deep in differential geometry, but since you brought it up, or actually I was going to mention it anyway, I can ask you some very basic differential geometry questions. If I was for some reason interested, it's not a physics problem, it's really a geometry problem, but actually physics is nothing but geometry in phase space. Okay, so it's actually all connected together. So if I had this, let's do it like this. So if I give you a curve z going from 0 to, let's say, z1, okay, and I would like you to measure the length of this curve. You know the formula for this? It's from some calculus or something. So what is the length? Think about it while I write it down. Of curve set t for t going between 0 and 1. And there's a very beautiful formula for this. Get my water in. No clues? It's a formula that uses exactly this thing. Because kind of, yeah?
Over 3 by 2 something.
No, it's not that. It's not that tricky.
Formulas actually.
I mean, like intuitively, how would you measure that, right? If you really had that job, well, a good idea probably would be to split this into small pieces, right? And then measure the length of every piece, right? And the smaller and smaller the pieces would get, the better and better approximation of the actual length of the curve would you get, right? And eventually you would get the exact thing by taking the limit, by making these pieces like infinitely small, right? So let's not dramatize this. I don't want to do a differential geometry course, and I don't remember all of that stuff anyway off the top of my head, but let me just write you the formula here, and that's exactly this. Okay, so if you integrate this norm of z dot t from 0 to 1, you get exactly the length of the curve, which is kind of cool. And also, as we already brought it up, there is a thing called arc length parametrization. Because sometimes when you study curves, you kind of don't care. I really wish I had the laser pointer here. Sometimes you don't care whether, like, imagine there's like a little car traveling along this curve, okay? But let's say you are not, you don't care about the speed of travel. Like if there's somebody crazy that goes like really fast and slows down and then again speeds up. Let's say you don't care about this, that you only care about like the geometry, about the actual curve that the motion traced, but not about that speed, okay? So in that case, what you can do, you can say we'll do an arc length parametrization, which means that you introduce another function phi or something, which is another real function, such that after you do z of phi of t, you will get 1 for each t, okay? So this means a time reparametrization, which will make the instantaneous speed at every time unit, okay? But it's not super relevant. It's related, but not super relevant to my main point. So this was really just to give you a geometric intuition of what it means to solve this simple system of linear differential equations geometrically, okay? And I guess I didn't completely put the pieces together. So because what we have so far is we have an understanding, geometric understanding of what the z dot t is, right? That's the tangent vector times the instantaneous speed. So really the instantaneous velocity of whatever is traveling there. And we know that this thing is nothing but a minus 90 degrees rotation, okay? So let's put these things together and see what it actually means to solve what. So now the question is, what does it mean geometrically to solve this system of ODEs? Okay, and the phase space interpretation looks like this. Okay, X and V, and we can to make it we can assume that we know Z0. Okay, we know when the motion starts. This is we know where the motion starts, but wherever we get, let's say that the ZT got like here, okay? Let's assume that things were all, or let's put it like this. If we are here, we know what the tangent velocity should be. What it should be. Okay, so if I am here, can you tell me the tangent velocity, the motion of this little car that's tracing this curve ZT should have? Exactly, it's exactly that tangent, right? So all I need to do is to draw like a little arrow here, right? And rotate that arrow. Rotate it like here, right? But because it's an arrow, I can draw it anywhere. I can draw it here because the car is right here. So this is the instantaneous velocity the car should have at this point, okay? This thing here, okay? Let's get rid of, oh no. Sorry, I'm still learning how to use this tool. So if the point was here, if my ZT happened to be here, maybe for some different t, where would the arrow be pointing? Well, somewhere like this, right? If it happened to be here, it would be pointing in the same direction. It would just be a little bit less intense. Okay, if the point was here, it's actually not going anywhere, right? Because that's 0, 0. Rotation of 0, 0 always gives you 0, 0. So that's the car when it's here at the origin is stopped. Okay. So what we have here, so this AZT actually defines a vector field. That's what I was kind of trying to visualize by drawing these arrows. What a vector field means is that for every point, whichever point I pick, vector field means that I have a vector associated with that point. Okay, this AZT gives me one way how I can compute that vector. There could be other ways too, okay, in general, but we are studying now this AZT case even for a special A thing. Okay, so I have actually for you a more interesting example of a vector field, just to show that a vector field can be anything. This is like a cooler example of a vector field. Basically, at every point, you have a little vector. That's the idea of a vector field, okay? And then what it means to solve a differential equation intuitively means that I start somewhere, okay? This will be my Z0 thing, okay? And then I pretend I'm like a little car, and every point this arrow gives me the instantaneous velocity, okay? So I start going, and the solution really means keep going, okay? Now I get into like a point when the arrows are a little bit smaller, so I'm going a little bit slower, okay? And I keep going, tracing these arrows, then the arrows get a little bit bigger, so I go a little bit faster and keep going, okay? That's exactly what means solving an initial value problem, because I am given this is at 0, and I need to trace the motion from there, okay? So that's really the idea. If I started somewhere else, just to say I started, I don't know, here, this would be my Z0. So again, I start going. Here it goes like really slow because these guys are like really, there's probably some singularity here, right? Then it kind of turns slowly and then it goes quickly and shoots up. And that's the solution, that motion. This is the curve ZT. If I got that, I have the solution of the differential equation and consequently solution of the Newton's equations of motion. I know exactly what that motion is. Okay, so for our case, we are looking at here, this A thing is simply this matrix 0, the minus 90 degrees rotation matrix, 0, 1, minus 1, 0, right? So the vector field looks kind of like I draw it here, right? There would be another vector there, there would be another one like this, and so on. So at this point, you should have enough geometric intuition to tell me if I start here, how the motion will look like, even without computing anything or doing any differential equations, anything. You should have a geometric intuition of how the motion will probably look like. So maybe raise your hands. I'll try to give chance to people who didn't speak yet, so everybody can gather up some activity, brownie points. What? Oh, sorry. Yes. Let's just start here. I mean, anywhere really. The answer is the same wherever you start. You guys have an idea? Let me start. Let me give you a chance because you're in the back, so you're kind of. Exactly, it would be exactly a circular motion. Yeah. So if I was to draw it, it would be something like this, and keep going, right? Forever. If I start at a different point, if I started here, I would get a different circle, but the idea is it would still be a circular motion. This thing actually has a really cool feature. So lets you draw a perfect circle. Amazing. It's not perfect because it should be centered here at the origin.
So basically showing geometrically that if we give it a big velocity kick from 0, it oscillates wildly forever. But also if we give it a large initial displacement, it'll oscillate wildly forever.
Yep, you are exactly right, and that's the beauty of the phase space. I was gonna get to this after we actually solved these differential equations. So that's a great point, but let's hold off on that until we solve it, like mathematically. But that you have a great point. Let me just postpone that discussion a little bit, okay, Magdalena?
I think that's probably what he said, but so that this would have a spring that's kind of infinitively bumping around.
Mm-hmm. Yep.
Have no damping.
That's exactly right. There is intentionally, I did not put any damping there, right? There is just this, where was my spring? My spring was here. So yeah, so indeed, if the spring starts here, then it goes like here, right? Then it's and then it overshoots, and there is no damping, so this motion just keeps going on and on and on. Oh, that's a very interesting question. Is it possible to create a system like this in reality? Well, I think you probably cannot get exactly that because there will always be a little bit of damping, but I think you can get the damping to be very small. I think actually a good example would be like planetary mechanics, right? Like basically that's how like the sun and the planets, it's more complicated of course than this oscillator, but they just keep going and they will keep going for quite a while, right? Now at that point, like relativistic effects and things like that come into play. But my point is that the Earth is gonna be spinning and you don't have to worry about that stopping due to some damping, right? Even though there certainly is stuff going on, right? But it's so small that it kind of doesn't matter. Like if you wanted the harmonic oscillator. So first of all, in any real spring, there would be like internal material damping, right? If you have like a muffler or something, and actual springs, then the material it always has a little bit of damping. But you could probably do something like with magnetic in vacuum tube kind of thing. I'm not a physicist really, but I imagine you could get pretty close to that. And that's really the magic of the Newton equations, that it really describes real world surprisingly well, right? It starts falling apart in like the cosmic scales where relativistic effects start to matter, or at nanoscales or where quantum effects start to matter. But in most scales, and that's all we really frankly care about in physics-based animation, the Newton's equations of motion are amazingly good approximation of what the nature seems to be doing. And why is it exactly second order here? Why is it like that? Newton just discovered that, right? But why is it like that? That's probably more of a religious question than scientific. Yep. Karen?
I have a question about the velocity vector. Why does it go in circle? I don't understand.
Oh, because it's the rotation. So yeah. So why in this case, why these vectors go like this, right? Why these arrows? If I give you a point here, why this arrow points in this direction? If I give you a point here, why this arrow goes like that? That was the question, right? And the answer is that's the first part here. That was the geometric intuition of the AZT. Okay, ZT, forget that's a function. For a given t, it's just a point. Okay, and that point gets rotated by this matrix A. The matrix A is just this. It's minus 90 degrees rotation. Okay. Now I'm brushing under the carpet some details. I don't want to make it super formal because formally, like from a vector field, would be assigning a point a vector. So at some point you would have to convert from a point to vector. But I think we don't have to formalize it further. So basically, for a point, you can draw this arrow here. That's like the associated vector. That vector gets rotated by minus 90 degrees, and that's your arrow here.
But why does it go in circle? I mean, on the left side of the coordinate, there's no vector velocity vectors there.
They're everywhere, right? Like that. This was just examples, right? If I go here, there is gonna be a vector like this, right? If I go here, there is gonna be one like that. Every point, wherever I pick a point, it has this little arrow. Like today, we could like nicely visualize it with computers. If we spend some effort, we could do like a really nice visualization, right? What I find amazing is like these Newton kind of guys, they were just like, all they had was pen and paper, I guess. No computing devices whatsoever, no visualization tools other than the paper, I guess. So it's good to kind of have a little bit of that same skill and be able to imagine it in your mind, because you will not be able to that's why I'm working out this 1D example, right? Because there in this 1D example it becomes a 2D ODE system, and there I can visualize everything, right? But if it's a 10,000 degrees of freedom piece of cloth, then all these visualizations become hard or even impossible. So there you are really stuck, or then you have to rely just on the math and some more vague geometric intuition. All right, speaking of math, what I wanted to do, so this was just the geometric intuition, right? But I want to connect it to actual hard math, to be not just hand waving here all the time. So I just actually want to solve this differential equation. Okay. So, all right, so where were we? We were saying we will want to find the analytical solution of this ODE. Okay. Do you remember? Does anyone know how to do this? This is the standard calculus stuff. This is a linear system of ordinary differential equations. In this case, just a 2x2 system, so very, very simple. Or does anyone at least remember the key trick there? The key trick is exponential, okay? So actually the analytical solution is kind of simple. You know what? Let me go to another page. So what we have, we want to solve the system of ordinary differential equations. What I want to do is to show you that the math connects to the geometric intuition in quite a beautiful way, okay? So this A is a matrix. It's a 2x2 matrix. We even know what matrix it is, right? This 0, what was it? 1 minus 1, 0, right? And the solution, analytical solution, is given like this. So Z of t is exponential, and that's the key word I was looking for, to ta z 0. Okay. So this thing is matrix exponential. So that maybe begs for a little bit of explanation. So this is a matrix exponential. Which means, I guess I could put it like this, that's a function that consumes a 2x2 matrix and produces another 2x2 matrix in our case. Okay, it could be also a larger matrix, but let's not make it more complicated. And how is that matrix defined? The matrix is defined like this, kind of like a regular exponential except for matrices. That is, I is an identity matrix plus m squared divided by 2 factorial plus m cubed divided by 3 factorial, and so on, okay? Just like a regular exponential except for matrices, okay? So this thing is an identity, 2x2 matrix, right? This thing is also a matrix. This thing is the matrix, what is m squared, right? M squared, of course, is m times a, but this is a matrix product. So again, 2x2 matrix, okay? So this is an infinite sum of a bunch of of infinitely many 2x2 matrices, which always converges. Is that true? It always converges?
Yeah. If the matrix is for number is true, but for matrix has a condition.
Let's see. Yes, it does. It has to. Yeah, but let's. Well, actually, oh no, let's get stuck on this. Let's look at it for our homework. It definitely does converge for this matrix. Okay, and that's all we need right now. I think in general you probably need some assumptions, but I'm not entirely. I don't remember what they are. But this is what the matrix exponential is, and the point is, if you compute it, and this t that's your time. That's this parameter here. And the Z0, those are the initial conditions, okay? That you get to pick whatever Z0 you want, okay? That's basically what's given to you, okay? So then the analytical solution consists in computing this matrix exponential and doing, so this again, this is just a matrix vector product, okay? And this, of course, to make it complete, this is just a 2-dimensional vector again, okay? So the question of solving the system of linear ordinary differential equations reduces to the question how to compute this damn thing, how to compute the e to m, okay? In our case, e to ta, okay? But we can think about the general matrix m. Do you know that? How to compute the matrix exponential? Matrix exponential is kind of funny, right? You certainly don't want to be computing it like this to evaluate infinitely many matrices and then sum them together. That's a bad idea. That was a joke. So there is a better idea how to do this. So if m is diagonalizable, and this is like a basic, that's where the linear algebra, that's why I said the linear algebra is a prerequisite. So if m is diagonalizable, that's the mouthful, which means that we can write m as v lambda v inverse, okay, where all these things are 2x2 matrices as a product, as a factorization of the matrix, okay, where v obviously is invertible because we are taking the inverse, right? That's what this thing means. That means that that's the inverse. And this lambda matrix is diagonal. So that means it looks like this. It means it looks like lambda 1, 0, 0, lambda 2. All right? So that's the definition of what it means that my matrix is diagonalizable. And if you had some linear algebra, then you know that some matrices are diagonalizable, some matrices are only diagonalizable in the complex domain. That's actually the case of this matrix for a very good reason. Some matrices are diagonalizable in the real domain. Do you know this kind of stuff? Like the nicest case, if I give you a real symmetric matrix, I'm just kind of trying to see how much linear algebra you have had. So let me ask you this way. if the matrix A is real and symmetric, is it always diagonalizable? That's, I guess, the most basic question to ask in this context. If A was real and symmetric. So this is definitely real, right? There are no complex numbers. Complex numbers are going to come up in a moment, but they haven't come up yet, so everything is real so far. It's definitely not symmetric, right? Oh, what is symmetric matrix? Symmetric means symmetric if M transpose equals M. Yeah, so like the basic linear algebra result is that every real symmetric matrix is diagonalizable, and even with special properties, it even has a you can even pick on the matrix V to be orthonormal and real. So that's the nicest case of eigendecomposition. Okay, that's also what's the basis of PCA or SVD, principal component analysis, or single value decomposition. But let's not dive so deep into linear algebra. Otherwise, I could easily convert this into a linear algebra course. And let's just assume this matrix is diagonalizable. Our A is diagonalizable. That's the good news. And I will actually compute the diagonalization for you. Not sure if I'll have time to do it today, but I'll see. But let's see if M is diagonalizable, how can we compute the exponential? Okay, that's how we actually solve the system of ODEs. So as I said, this exponential is this, right? I plus M squared divided by 2 factorial and so on, okay? Now if I plug in this thing, okay, so now I use the fact that M is diagonalizable, then I can write this in a funny way, okay? I can write it, so the identity I can write as V inverse, okay? Because matrix times its inverse is the identity, okay? Plus, and then M is just V lambda V inverse, okay? So this is what used to be the identity, this is what used to be the M, right? And then I have M squared divided by 2 factorial, okay? So this is the 2 factorial. Well, M squared means M times M, right? Which means V lambda V inverse, V lambda V inverse. And you're like, aha, wait a second, V inverse V is identity, right? So this whole thing becomes just V lambda squared V inverse, okay? This whole thing becomes just that, okay? And the same thing happens for the other terms, right? Then I have M cubed, but again, what happens is that these middle terms, they just erase themselves, and I just get the powers of lambda, okay? So this whole thing I can write. Did you not have this in some calculus or something? Who has seen this before? Show of hands. Okay, about half of you, I guess. It's not that hard, really. So I can write this whole thing like this. Identity plus lambda squared divided by 2 factorial and so on, infinite sum, V inverse. Okay, is that clear? That's just distributivity of matrix multiplication. All right, so now what is this thing? So first of all, what is lambda squared, right? I said that the oh shit, the other one. Lambda is this, so that's a diagonal matrix, right? So what's a lambda squared? Yeah, somebody just yell it.
The squares of all the
Exactly, squares of all these. Lambda 1 squared, 0, 0. Lambda 2 squared, right? The same thing for the third power and so on. So what is this thing together? Actually, that's the key thing there. What's that infinite sum with the lambda matrix? The lambda matrices are now diagonal, okay? Diagonal matrices are very simple kind of matrices. Karen, or? It's better to raise your hands because I try to give everybody a chance to speak as opposed to just the few ones who are quickest on their feet. Yeah.
With each element being 1 plus lambda 1 plus lambda 1 squared, and then so on down the diagonal, which is the exponential expansion of each.
That's exactly right. So this matrix is going to be exactly the exponential of the exponent of lambda. Now we are talking about scalar exponential, okay? So just a scalar exponent. 0, 0, e to lambda 2. Okay, and that's because this thing here, those are just diagonal matrices. Okay, so this really is just nothing, just bunch of independent numbers. This is just way of writing the same thing for lambda 1, lambda 2, lambda 3, and so on. Okay, so this is that. So if we have the diagonalization, then we can compute the matrix exponential just like this. Okay, computing this matrix, that's a joke, right? If I give you a diagonal matrix, computing. Do anything funny again? Ah, no. Wait. Oh, good. Still works. I was worried it stopped working as before. It was just the palm rejection thing. So now computing this, if you know what lambda 1, lambda 2 is and what v is, that's a joke, right? Because computing the exponential, that's a simple matter of calling one function. So the scalar exponential is no problem. The matrix exponential is a bit of a bigger problem. So now we are left with the question how to diagonalize our matrix A, which is our old friend 0, 1, minus 1, 0. Okay, how to come up with this thing? Okay, how to come up with the V and lambda such that this gives me A. Okay. If we do this, we know we can solve the ODE. We will get the analytical solution, and if we are lucky, hopefully the analytical solution will match our geometric intuition, and everybody will live happily ever after. So how to diagonalize A? So that means that we need to find the V and lambda such that V lambda, the inverse, gives us exactly A, right? Any ideas how to do that? Compute the eigenvalues and eigenvectors. That's exactly right. So here comes, I guess, the quick linear algebra recap. So that's why I kind of like this, because it like connects a bit of calculus with linear algebra. So it's also like a good like a recap session, I guess. So let's talk briefly about eigenvalues and eigenvectors, because that's the key to diagonalizing our A matrix. Okay. So how is it defined, an eigenvalue and an eigenvector? So eigenvalue and eigenvector pair, let me give this a little arrow to make it clear it's a vector. So if this equation is satisfied, then we say that lambda is an eigenvalue and V is an eigenvector. There is one important assumption which I forgot here. What is that? So maybe look at this, right? So this is matrix times vector equals scalar times vector. So maybe I should say let's not complicate. No, let's do complex. Really, that will be better. So the eigenvalues and eigenvectors, they can be complex. It's useful to consider complex ones. Okay, so if we are, let's just say that the A is still 2D. So let me make the dimensions clear. So this is 2 by 2, this is 2 by 1. This is a scalar, so 1 by 1, if you will. And this is a vector, meaning 2 by 1. Magdalena? Yeah. That's exactly right. Yes, the Austrians are very good in like this for formalization thing. I remember my linear algebra professor was joking something about this, that like they were learning like all these like axioms and had to like remember like the vector space is like defined by a laundry list of like 10 properties, and my country was part of the Austro-Hungarian Empire, so this culture of like remembering all these things precisely is still there, which is kind of fun historical insights. But the mathematical bit is that the eigenvector must not be 0. And there is a good reason for it, because if you allowed 0 eigenvector, then that would be trivially satisfied. Basically, of course, if you put 0 there, then A times 0 equals whatever the lambda is times 0, right? So that's absolutely not interesting, okay? So we need to rule it out. There's another geometric reason why we want to rule out the 0, and that's because the eigenvector, the interesting thing about the eigenvector is its direction, not the magnitude, Okay, and that you kind of see immediately, because if V is an eigenvector with eigenvalue lambda, then alpha V for any alpha real is also an eigenvector with the same eigenvalue. Okay, so the scale of of course, right? Because if I just multiply this by alpha, then nothing really changes, right? This thing is still holds. So alpha V is still eigenvector with eigenvalue lambda, still the same eigenvalue. Okay. So the scale of the eigenvector doesn't matter at all. But what you don't want to, unless you made it 0, okay? So basically it's like the geometric notation, the eigenvector is an arrow, and you can scale it up or down, but you better don't scale it to 0, because then you cannot get the direction out of it anymore. That's the idea. So this was just like a refresher of what eigenvalues and eigenvectors are. And now what we need to do is to find them for our matrix A. So let's do the usual setup. So if we have our matrix A, so in our case the A, if we have a given matrix A, such as this one, how do we find its eigenvalues and eigenvectors? Because the answer to the diagonalization is hidden in the eigenvalues and eigenvectors. It's not that much hidden, it's there. So we need to find the eigenvalues for our matrix. And how do we do this? Well, we have to kind of find the V's and lambdas that satisfy this, right? So to do this, you have probably seen that before. We just move this on to just do this, right? This equals like 0 vector thing here. So I can rewrite this as A minus lambda I V equals 0. Maybe I will not do the vector thing on the 0. Why did I put the I here? Because lambda is a scalar, right? So scalar plus matrix would not be defined, right? So that's why I have to put, that's a 2x2 identity matrix, right? So this has to be equal 0. And so what does that mean? That means that this matrix needs to be singular, okay? And the condition for singularity can be expressed by determinant. So that means that the determinant of A minus lambda I must be 0. If I have to have any chance of finding an eigenvalue and eigenvector, then the determinant of A minus lambda I better be 0. Okay? Now, we are almost out of time, so I'll certainly not finish the whole thing here, but I can at least get it started, and then you can try to finish that for your homework, which I will not be grading because I promised not to do any homeworks, but it would have been a great homework. Just to kind of brush up your linear algebra. So, but let me at least compute the determinant here. A minus lambda I. So what is A minus lambda I? So A is this, right? This is A. So if I do minus lambda identity, then that is minus, oops, sorry. Then it's minus lambda, 1 minus 1 minus lambda, right? What's the determinant of this? Lambda square plus 1. That's exactly right. I assume everybody knows the determinant of a 2x2 matrix. So what are the solutions? Lambda square plus 1 equals 0. That's this thing we are solving for this particular case, right? What are the solutions there? And there's this little trick you have to do here, right? Yep. I and minus I, exactly. So clearly there is no solution in the real domain, but we have to go to the complex domain. And that's not a coincidence, that's because we are dealing with a rotation, okay? So the solutions here are complex, but that's okay. We'll just do complex eigenvalues and eigenvectors. That's what we really have to do because we need to get rotation out of it, okay? So don't be scared or surprised that we have to deal with complex numbers. Complex numbers and rotations are like brothers and sisters kind of thing. Siblings. So yeah, so the two eigenvalues are plus and minus I, the complex unit. And what we need to do now is to solve for the eigenvectors. and I'm out of time, so we will do it not next week, but the week after the next week, or maybe no. I want to go over the project topics on Thursday. We'll not have any class on Tuesday because the SIGGRAPH deadline. So we'll do it the week after the next week. So actually, if you want to work this out for your homework, which I will not punish you for not doing it, but if you do it, then you will be happy. So what you need to do is to find the eigenvectors, which will tell you how to get this decomposition, which will in turn give you the exact analytical solution for Z. All right, so let's stop here. Do you have any questions? I can stop the recording.